Alright, so today's video is going to cover connecting the zinc processor. Um, so the zinc processor has those dual ARM cores, and we're going to be able to run a C language or assembly language program and somehow magically connect that up to our 7-segment display. Now, if you've done microcontrollers classes, you probably have done this already, where you've written some C code and you've managed to change the state of the hardware. And we do that through memory mapped I/O. Where there's some kind of shared bus between the CPU running the C code and the hardware. And by doing loads and stores, we can essentially store values onto the memory bus, and then the hardware interprets that to map it into its internal registers, where we can even read the status of that hardware and back into our C program. So it really turns out to be load words and store words are the way that that happens. So this video is going to talk about developing this wrapper that goes around our 7-segment controller. So in the previous videos, what we've done is we've actually built all of this stuff here. Let me erase all this. And in a previous video, we made a really simple BCD to 7-segment controller. And the way that that guy worked is he took 4 BCD values in, and he drove out the 7-segment cathodes and anodes. That's all well and good, but I would also like to be able to have a raw bitmap where I can send in essentially the 7 anodes and 6 cathodes, or maybe it's 8 anodes, 9 anodes. I think it's 9 anodes, whatever the number of anodes is. Let's see. Be able to erase. Make this all right. I'm getting used to this new tablet. This is all really spiffy. So 9 anodes and 6 cathodes. And I want to send those in as just a bitmap, ones and zeros, and have that translated out to the cathodes and anodes. And then maybe I really want to be super fancy, and I want to be able to have a timer. So I want to be able to do a time display. And then I want to be able to send in hours, minutes, and seconds. I will also be able to read hours and minutes and seconds so I can keep track of the current time. And I want to control the display to be 12 hours or 24 hours. And I want to turn that into, well, I don't want to turn that directly into the cathodes and anodes. I've already got a utility that can do that. I've got my BCD to 7-segment display. And so what I really want to be able to do is somehow connect that into there, and so have the hours and minutes and seconds here in BCD, and then reuse this piece of hardware over here so that I don't have to redo all of that. So that's kind of the logic of what we're going to try to build. And to make this all happen, all of this needs to somehow get its control signals from C language, from the memory map, from memory loads and stores. And that becomes the grand challenge. How do we make that happen? Well, to make that happen, what I'm going to do is I'm going to have my peripheral that sits on the Z board's AXI bus. And that's going to give me some number of registers. We're going to pick 4 registers. And what I'm going to do is I know from the timer I need to keep track of the number of clock ticks per second and the number of ticks per the blinking of the colon blink. Kind of sounds like a disease. And so what I'm going to do is I'm going to use two registers for that. So this one here is going to be a 32-bit register for the second period. And this will be for the colon period. This register, what I can do is I can use this to store BCD values. And so if we chunk this thing up into bytes, we actually have, if we do this into bytes, divided up into 4, because we have byte 0, byte 1, byte 2, and byte 3. And I could further subdivide this down into the nibbles, the half bytes. And for instance, this could be digit 0, and this could be digit 1, digit 2, and digit 3. And in this mode, the blue mode here, will be my BCD display. And so when you think back to what we've done before, I would take these 4 wires and connect them into the BCD display for digit 0. And those 4 wires go out to digit 1, and those 4 wires go to digit 2, and those 4 wires go to digit 3. And remember, these registers are really built on flip-flops, and so they're just going to store those bits. And so I could easily have the existing bitmap BCD controller that we've already built work with those. I could also reuse these and use this to store my seconds and my minutes and my hours for the time. And it just depends on whether I want to do time or if I want to treat it as BCD, or even if I want to treat it as that bitmap mode that we saw earlier. So if I do the bitmap mode, I know that I need 15 bits to store all of those values. And so, for instance, I could use up here in this register 0 the most significant 15 bits, and then those 15 wires would go down directly to drive the cathodes and the anodes. So by writing a value here, I could set whatever values I wanted to set. Just like if I write a value into here, I could set a value into the BCD input to the BCD controller. Finally, what I can do is I can pay attention to the idea that I need to be able to pick one of these modes. And so mode 0, for instance, might be the bitmap. Mode 1 would correspond to the BCD display, and then mode 2 could correspond to my time display, and mode 3 could be future use. And so I could just arbitrarily, I'm just picking these things, bits 1 to 0 would be the mode. And if you're in mode 0, then we're going to drive these values out to the anodes. And if you're in mode 1, we drive these through the BCD controller and out to the cathodes and anodes. And if you're in the mode 2, you're in the time interpretation. But then we'll have to take the time and drive it into the BCD module, and then the BCD module will drive the cathodes and the anodes. Now the time module has one further complication, and that is we like to store time as either 12 bits or 24 bits. And that's also kind of one of those status registers. And so we'll make register bit 2 here be 12 or 24. Now, this is all going to be what drives all of the rest of these control units. I can also read from these things, and so we're going to have one extra complication, and that is reading from this register will either give BCD value that's been stored or current time from the time controller, the timekeeper. So we're going to try to build all of this, and this seems really super complex, but if we really just kind of layer up the design here, it won't be too bad. So remember, to layer this thing up, where we're going to start is I need to have those cathodes and those anodes being driven by something. And typically what we're going to wind up with here is some kind of a multiplexer. I'm just going to draw them all coming off the same control line. And that's going to be selected by the mode. And so if I'm in mode 0 or not 0, so we'll call that 0 and 1. If I'm in mode 0, the source for the cathodes and the anodes comes from the bitmap. If I'm in source 1, it's going to come from the BCD to bitmap. And just like I have here, I have that BCD to bitmap. Or BCD to the cathodes and anodes. It had BCD in, and I'm going to have one more multiplexer here. That's also going to be driven by the mode. And in this case, I'm either going to pick the BCD registers, or I'm going to pick the time. And so with this simple little arrangement, now I can very easily build this module in Verilog and have one module that manages the time, one module that we've already done that manages the BCD. This bitmap is really just the registers, and so then there's just a little bit of glue logic to figure out which path I want to take. Create a basic block diagram project. And what I'm going to do here is we're going to call this 7 system. This is going to be the system that holds the Z, it holds the IP modules that we're going to create, and eventually it will even hold the C files that we're going to use. And I'm just going to create this like we've been creating other projects before. Whoops. And now that I have that, what I want to do is I want to go through here and create a new IP module. And what this is going to do is it's going to run a wizard that's going to allow me to fill in some basic details here. So we're going to call this like 7 segment, sorry, we'll call it a 7 seg controller. And it's going to be advanced 7 segment controller. Wow, yeah. And it wants to know where do we want to create this IP location. And by default, it's going to put it into the parent directory. And so this is kind of the default configuration for the AXI light bus. We have a 32-bit wide data path. We have 4 registers that we're going to be able to use. And when we're all said and done here, it's just going to write out a bunch of files, and it's going to write them into a IP directory. Okay, so what I want to do very briefly is pop open a window here and take a look at what it's done for us, because I think it's important to understand the relationships between all of these different files and locations. This is the system that we've created, and for instance inside here are the files that are being used by the design that we launched here, this 7 system, and it's basically empty. Now what I've done so far is I've created this 7 seg controller, and inside this 7 seg controller there's just a bunch of like little Verilog files that are part of this IP. But if you notice what's missing, there's no project file. There's no obvious way to edit these things. But the important thing is I have these kind of header HDL files here. Those are the magic that makes all this work. So one thing I can do is I want to kind of get a project that lets me edit these things And in the previous video that I did about creating these, what we did is, just going to park this over here. What we did is we went to the IP catalog and we went to the user repository and we found the module itself, and we right-clicked on it and did this edit an IP packager. And what this does, unfortunately, is it creates a temporary project. A project that has all of the configuration inside this existing system or 7 system. That's not really what I want to do, because then I can't continue to develop this, because every time that I go to edit an IP packager, it overwrites the IP. But I do now have, so at least at this point now, what I have is I have the Verilog files for the AXI bus, right? So I can kind of put this project on hold for the time being. And in fact, what I'm going to do now is I'm going to make a whole new project. I know this is really kind of a bizarre way of going about this, but really what I wanted to do is get that wizard to write out those AXI Lite files for me. And so now I can create a whole new project. Now this isn't going to be in that IP repo. This is actually going to be the 7 controller. That's the name of this project. And I'm not going to even bother creating anything at this point. I guess I could pick the Z board, and we're going to close the system project. And now I'm in the 7 controller project. Okay. And what I want to do is I'm going to start off and bring a bunch of files over that I've already created. So, for example, in the previous video, we had made a BCD controller. Remember, we had done the 7 segment mapping the BCD values onto the shared cathodes and the anodes. So I'm going to go ahead and I'm going to add those files, and I've got them sitting on my desktop right now. We needed that BCD to 7, we needed the BCD controller. Here are those AXI definition files. This is the top level module, and then this is the lower level AXI module. And we even, I guess, could even have some simulation files. I'm not going to bother bringing those over for the time being. And I want to make sure that I say copy these into the project. And so it's going to copy all of these source files into this project. All right. So this is the AXI definition file that Verilog, or that Xilinx created for us through that wizard. And we see here is a bunch of input and output wires that are used to connect this module to the outside world, and then they're just passed directly into this 7 Seg controller, this next level down. So if I expand this tab over here, we see that there's a user module underneath all that. Now, I have my BCD controller, and that BCD controller, remember, we had created in the previous video. And I'm going to just kind of bring that over here. And this is the module that's going to essentially have whatever our BCD values are. Well, the catch is that I need to have the BCD values come from somewhere. Before, we wrote a driver program that just did a counter and it drove those values for me. But now what I want to do is I want to connect the values to display to a register, one of the 4 32-bit registers that we're going to manage in with this AXI bus. And that way I can connect to it from C language, write values in those registers, and then the 7-segment display will display them. That's the idea. So what we've got to do then is to modify this AXI bus to expose values from those 4 registers and bring them through. Let's take a look at this module here for a second. So I'm going to go into this module, and I've already added some stuff to it, so we're going to kind of start up here. These are the basic signals that are part of the AXI bus itself, and I haven't changed any of this stuff. The way that this thing works is it detects when you're writing to the bus, and we'll look at that in just a moment. And when it detects that you're writing to one of the registers, it will copy the values from the AXI bus's write data lines into the appropriate register. So these slave reg 0, 1, 2, and 3 correspond to the 4 slave registers that I created with the initial wizard. And so what I want to be able to do is I'm going to say take the slave reg 1 and take the lower 16 bits of that register and turn them into the BCD values that go out to the BCD controller. And to do that, go back up to the top here, and under the user ports, I'm simply going to expose those 16-bit values, right? And now those are just wires, and I need to connect them to something. And so way down here, the BCD values, I'm going to simply assign to the slave reg 1 values. So back up here into the top, this is that AXI module, and here are all the control lines. And so what I need to do here is to create a wire called BCD values. And remember, I'm going to go back over to this. I'm sorry to jump around so much. Let's go back up to the top. So we're copying whatever these lower 16 bits are. We're just kind of copying those onto those wires. It's not really a copy. It's literally a wire. So they have the exact same value, and they're going to be output of this module on BCD values. All right. So now if I come back here, I can do we can do it at the top or the bottom. It doesn't matter because of the naming conventions. So I could do BCD values, BCD values. Now, the other thing that I've got to pay attention to is the AXI bus uses a negative logic reset. And so my modules, typically the way I write them is that they use a positive edge reset. So if reset is high, we're in reset. I think that's the name of the signal. So yeah, it's S. Make sure I typed it in right here. Yep, okay. So I'm just going to assign my reset signal to be the negation of the AXI bus reset. That takes care of that. Look, there's our BCD values. And now we have to deal with the anodes and the cathodes. And just as I did before, I have to be able to turn them into input and output variables. And just as I did at the end of that last video, or the supplement, I'm going to use that in-out parameter to this module and either drive ground or high impedance. And so this is exactly the code that we had before. I just want to fix the tabbing here. And so let's see, we have that going on, and then the last thing I need to do is make some wires. So I'm back up at the top of this module, and I'm just going to insert those in-out anodes and cathodes. And the last thing to do is to connect the BCD controller. So we call this BCD anodes, and this is BCD cathodes. Oops, and that should be semicolons, and they're just wires. Sometimes copying and pasting can get us into trouble. All right, so at this point, we've kind of just done what we did in the previous video. We wrapped the simple BCD controller around this top module that also enrobes this AXI controller down here. And what I've done is I've made it where I can simply write a value into a register, and this BCD controller will suddenly get input on the values, and it will do its normal job of mapping those BCD values into our 4 7-segment displays. It will manage the clock. It will drive the clock values to be whatever they did before. It does everything that it did before. Only now, instead of having the driver do that, the values come from the AXI bus. Alright, so in the previous step I showed how to integrate the BCD controller, and we just talked about the next step. So now what I want to do is I want to be able to add additional types of 7-segment controllers here. And so we're going to add, from that same directory, I want to add my raw bitmap controller. And this time I'm also going to add a time device, so I can turn my 7-segment display into a clock. So to do just what we did before, I need to be able to now integrate these other modules. Well, to integrate, for instance, the bitmap controller, I can, let me go back down here to the bottom. Our bitmap controller is going to have its bitmap values, and the bitmap values so the bitmap values are going to come from the AXI device. So I need to be able to define those wires up here, and I'm going to connect them to the AXI device just like I connected them before. So if I look at the AXI controller here, I'm going to add output wires. Looks like they're 15 bits wide, so let me fix that. I'm going to add the 15-bit wide bitmap values as an output to this module. And so down in here, I'll connect these 15 wires with the output of this port, and these 15 wires I assigned to be the upper 15 wires of slave reg 0. So writing to the upper 15 wires of slave reg 0 means that these bitmap values carry out of this module, this inner module here, and they carry out to bitmap values here, and the bitmap controller takes them here and translates them into anodes and cathodes. And we'll just take a look at that very briefly. Very simply, all it does is it splits them up into, whoops, the cathodes are the lowest 16 bits, and the anodes are the upper, the cathodes are the lower 6 bits, and the anodes are the upper 8 bits, 9 bits. I might have a bug in there. At any rate, the bitmap controller has the job then of turning those into anodes and cathodes. And so here we have the bitmap anodes and cathodes. And now I've got a problem, because I was generating the anodes and cathodes out from the BCD, and now I need to pick which one do I want. Do I want the bitmap values or the BCD values? Well, to pick, I need to have some kind of a mode selection. I need to be able to pick, are we writing BCD today or are we writing bitmap today? And so to do that, I need to be able to map one of my values from the AXI bus into a mode. And I've already done that here in my code. So what I've done is, I have a mode register that's connected to the least 2 significant bits of slave reg 0, and those 2 bits need to be brought out down here. So I need to have a mode, and we're going to connect the mode. Now remember, these values are these 2 values are driven directly by the lowest 2 values of whatever you've written into slave reg 0. And so now that I have that mode, what I can do here is make another set of wires, and I'll call those selected cathodes and selected anodes. And then I can have an assignment statement that says selected cathodes is equal to, if mode is equal to 0, then that's going to be the bitmap mode. Otherwise, it's going to be the BCD cathodes. And then I can do the same thing here for anodes. Now the ordering of these doesn't really matter, just as long as we define it before we use it. So I don't need the selected cathodes and anodes until right down here when I do these generate statements. Because the generate statements now are going to, instead of using BCD, they're going to use the selected. So now if you change the mode from 0 to 1 or non-zero, you'll go between bitmap and BCD. Alright, so at this point I just want to walk through, I've integrated all 3 different types of controllers. And so I have a mode that's large enough to select between the 3 different types, BCD values, bitmap values, and then the various clock values that are going to come out of this timer controller. I've connected them to their corresponding parts on the inner module, and we'll take a look at that in just a second. And then here, just like we did the selected anodes and cathodes, I'm also selecting which BCD values I want to pass into the BCD controller. If I'm in mode 1, that would be the BCD values directly from the AXI registers. If it's not mode 1, then I want the current time coming out of the time controller. The BCD controller we have already looked at. The bitmap controller we've already looked at. This timekeeper is something new. This is the timer. It's basically going to tick away seconds into minutes into hours. You have a control bit for 12 or 24 hours. I have a line that says we're going to set the time or we're not. And then it takes in 2 periods, one for the number of clock ticks per second and one for the number of clock ticks per colon blink. And so it's going to blink the colon periodically, and it looks like I'm missing a line here as well. I really should have colon out. And then here we have our selected anodes and our selected cathodes, and they're going to come to us from either the BCD anodes and the BCD cathodes. I guess theoretically over here when we do our BCD values, I would also want to somehow map in the colons. I'm not going to worry about that for the time being. But that's basically what we've got going on. And then there's our generate. So essentially we have some multiplexers to select one or the other. Multiplexers to select one or the other. I'm going to drive into this lower level module. Now remember, the Xilinx wizard created everything except for these user ports. And so here's the mode, the bitmap values, the BCD values, and all of those time values. And I'm going to be able to shoot right down to the bottom and skip over everything that's inside the Xilinx module except for this assignment of values to outside ports. So for example, when I want the mode, I'm just linking that to whatever bits are stored in the slave register 0 lowest 2 bits. Bitmap value, the upper 15 bits. The BCD value comes from slave reg 1. The seconds come from slave reg 2. The colons from slave reg 3. Whether we're in 24 or 12-hour time comes from slave reg 0 bit 2. The hours, minutes, and seconds come from slave reg 1. And then the only thing that doesn't come from the outside world is whether or not we're setting the time. That comes from this interior signal, this update time signal. And what that is it's going to be a single little burst that says change the time. And what I've done to make that happen is I'm back up here at the top and I'm scrolling down and I'm finding the part of the program where the slave registers are being assigned. And it looks like we're going to begin it right here. I've created a register called update time. It starts off at 0. Whenever the clock ticks, update time goes to 0. And if you are writing to slave reg 1, then update time goes up to 1. So this will stay on for one whole clock cycle, which is enough to trigger the timekeeper to update its internal value to match whatever has been stored into slave reg 1. So at the next falling edge of that clock, this also falls, and then the timekeeper begins counting away as usual. Everything else is completely the standard. One other thing. When I'm reading, I want to be able to read the current time. And so to do that, when I'm reading back from slave reg 1, I'm selecting, if you're in mode 2, which is the time mode, slave reg, oh, that's not right. There's 24 bits there, so that should only be 8 bits of 0. The current hours, minutes, and seconds will be read from the timekeeper instead of the contents of slave reg 0 or slave reg 1. If you're not in mode 2, then you simply get the contents that you've previously wrote into slave reg 1. So there it is. There's the structure for this this controller. Now, one of the things I want to do in this video is to go through as far as the synthesis to make sure that I don't have any errors in my code. So alright, so I kind of expected an error. Synthesis finished and it comes back and says view messages. So if I go back and view the message, it comes back and says well, that's not the error I expected. So I have a duplicate port. And we'll go ahead and synthesize again. I'm expecting an error in my Verilog code here. I want to get this right because, okay, so here we go. We have a mismatch in the width of these. Here we said it was 8 to 0 and 5 to 0, and in the BCD control we said that they were 6 to 0 and 8 to 0. Alright, so we better make sure that those are all right then. I'm kind of thinking there was 1 through 6 that would correspond to 0 to 5. I think that's actually correct. That should just be 5. Yeah, that should just be 5. Okay, looks like we have another duplicate port. That's where I fixed that. Okay, so this is the error message that I really wanted to get to. The way this timekeeper module is designed is every time it detects a carry from a previous adder, it triggers the next logic down. And the problem with that is that in simulation this is fine, but when it goes to simulate, it's trying to simulate that latch logic that the FPGA hardware just does not do well with. So instead of doing what I've done here, which is to say that this module is triggered whenever the carry minutes rises, or I'm in reset, or I'm in set time of 1, what I really need to do is to make this thing triggered on, say, the clock. And what that means then is I don't want to continually have set time running full tilt, or have carry minute run full tilt every time that there's been a clock tick. And so what I'm going to do is I'm going to remember that I want last carry minute. And whenever I'm in reset, last carry minutes equals 0. And whenever I'm setting the time, I'm going to reset that as well. And then inside here, instead of just asking whether carry minutes was high, what I want to also ask is if last carry minutes was low. And then if you notice, what's going to happen is this would tell me on the rising edge, the last time the clock pulses was 0, that this time it went up to 1. And so what I want to do then is remember what whenever I do this, I want to have last carry minutes be remembered. And so before this module ends, this last carry minutes will be assigned to be carry minutes. So then I'll be able to have this triggered exactly once. And now this little design pattern here of using a last register to remember the last time I went through this logic, comparing it to the current value to detect an edge, allows me to get away with that non-level triggered sensitivity.